As we've said before, reactions that form carbon-carbon bonds are some of the most powerful reactions that we can use in organic chemistry, because if we're trying to build larger molecules from smaller molecules, forming carbon-carbon bonds in specific places is a critical step there. And usually people that come up with new methods of forming carbon-carbon bonds, such as George Wittig. He's a German chemist, or was a German chemist. The Germans pronounce the W as a V, so this is the Wittig reaction. George Wittig in 1954 came up with this reaction, or discovered this reaction, or invented this reaction, however you want to say it. And then a couple years later, 1979, it always takes a lot of years to get to this point, he won the Nobel Prize. Why does it take so long? Well, he invented the reaction, and then they realize 10, 15, 20 some years later how valuable this reaction is, and what, in using it in organic synthesis. And so by then it had been used many times, and at a critical point where a carbon-carbon bond needed to be made. So let's take a look at what the overall reaction is. We're starting out with, here's our carbon chain. So this is a 2-carbon chain with a halogen on it, and we are adding to that reaction, or to that alkyl halide. We're reacting on phosphorus nucleophile with it in an SN2 reaction, and forming some sort of intermediate, which we're using a base here to deprotonate it. And then, so this 2-carbon piece then is reacting with a 1, 2, 3-carbon aldehyde here. And so a 3-carbon chain plus a 2-carbon chain. In the end, skipping to the end here, we have a 5-carbon chain. So without going through the mechanism at this point, we are realizing that the 2-carbon piece and the 3-carbon piece are joined together in a new carbon-carbon bond, and that new carbon-carbon bond was exactly where the carbon double bond oxygen used to be. Okay, so that's the overall what happens here, but let's look at it in a little bit more detail. So first of all, this abbreviation, I can't remember if we've introduced a pH as an abbreviation before, but pH equals a phenyl group. So it's a benzene ring. And so this reagent right here it's got a phosphorus with 3 benzene rings attached to it, and it is triphenylphosphine. And I guess that's worth writing out here. Triphenylphosphine. And it's a phosphorus that has 3 things attached to it. Periodic table, phosphorus is under nitrogen, and so if we had a nitrogen with a lone pair on it, then we would say that that was a moderate nucleophile. And a phosphorus, which is a bigger atom and less electronegative, is going to be a better nucleophile. So this is about as good of a nucleophile as you can get without having a negative charge. Most of the good nucleophiles, what you've been taught is it's not a good nucleophile unless it has a negative charge on it. But this is a fairly large electropositive element with a lone pair on it. And so this can undergo an SN2 reaction, where it comes in and with an alkyl halide comes in and kicks out the halogen. So let's make a note somewhere here that this is an SN2 reaction, and you know what the limitations are on an SN2 reaction, right? The alkyl halide, the alkyl halide must be either a methyl, the alkyl group must be a methyl, or a primary, and after that, then it could be a secondary, but you have a pretty bulky nucleophile here, and you start getting elimination there. So So in this reaction, will be limited. The alkyl halide will either be a primary or a or methyl. So bromomethane or yeah, something like that. Okay. So if a neutral nucleophile comes in and kicks out a leaving group, then the net product is going to have a positive charge there. And then, so that's step number one of the reaction, is dumping in triphenylphosphine with the appropriate alkyl halide. The next reagent we add is called butyl lithium, and it's a carbanion, like a Grignard reagent. Butyl lithium. And that is a very strong base, right? We have an electropositive element that has a lone pair and a negative charge on it. It's going to be extremely reactive. This doesn't want to have the negative charge. It wants to get rid of it. And so what happens here is, it's interesting, and again, nothing that you would be predicting off the top of your head, but I'm going to cross out one of these hydrogens and draw out the bond here so we can look at the mechanism. It pulls off a hydrogen that is on a carbon right next to the phosphorus there. So come in, pull off that, and so this is acting as a base, and this is acting as an acid, and so that is being pulled off, and the electrons are going to dump onto a carbon. And you think, well, what the heck? The carbon CH is not acidic at all, or shouldn't be acidic, and so why are we pulling that off? Well, first of all, we have a really strong base, and secondly, that once we pull that off, there's actually a resonance structure, and that resonance structure dumps the lone pair in here to form a double bond. So we have the three benzene rings attached to phosphorus, and then the phosphorus is double bonded in one of the resonance structures to this CH, which is bonded to the CH3. And so this is an interesting species here. What you see, I shouldn't have drawn out the bond here, because there's actually, if I'm going to draw out the bond, then I need to draw out all three bonds to show the three benzene rings that are attached. So we have three benzene rings and a double bond to carbon. We have violated the octet rule, and this might disturb you for a second until you realize that we are now in the third period, and we can have expanded octets using d orbitals. And so phosphorus is one of those things, like sulfur, that can have an expanded octet. So here's the resonance structures, two resonance structures, one where we have formal charges here and complete octets, and then here we have no formal charges and we have an expanded octet. But these are and you can put brackets around showing these resonance structures. Also, this is an interesting species because it's stable because of this resonance structure, with a negative charge on an atom next to a positive charge on another atom. And you don't see a lot of these things existing. One of them would be a nitro group, where you have a positive charge on nitrogen and a negative charge on the oxygen that's attached on the nitro group. This is called an ylid. So an ylid is a species that has opposite charges on neighboring atoms. Okay, bottom line is that we have created this carbon right here. Used to be an electrophilic carbon, partial positive charge on it, partial negative, so it used to be an electrophile, and now that same carbon with a hydrogen pulled off and a phosphorus on it is now a nucleophile. So we have created a carbon nucleophile. Just like a Grignard reagent, this is a carbon nucleophile, a carbon with a negative charge on there. So the next video we'll move on to the next step of the reaction, and if you want, you can anticipate and draw the curved arrows and then see how you did when we go through the next video.